Okay, so in this example, we have a compressor that's taking in nitrogen gas at 1 atm and compressing it to 10 atm. So it's doing work onto the gas, and we know that this compressor requires 250 kilowatts of power per kilogram of nitrogen gas. And we asked to compute the efficiency of this operation. So let's go ahead and draw a diagram. So we have a compressor that takes in a stream of nitrogen gas at 1 kilograms per second, and their output by conservation of energy is also 1 kilograms per second. So other information we are giving in this problem is the temperature and pressure of the entering gas. So the temperature is 20 degrees Celsius, the pressure is 1 atm. On the outstream, we have the pressure is 10 atm. So our input energy, you're told, is 250 kilowatts per kilogram. Our output is work done by the system, and that can be represented by PV. So we are asked to compute the efficiency of this process. So we know the efficiency is equal to simply output over input. We already know our input, and our goal is to compute the output. So step 1, compute work done onto the system. So work done is simply PV. But in this case, pressure and volume are changing entities. So we have to do integral. And to help illustrate this process, I'm going to draw a PV diagram. So you have volume on x-axis and pressure on y-axis. So we know state 1, the pressure is 1 atm. Let's say the volume is V1. State 2, the pressure is 10 atm. The volume, call it V2. So here I'm going to make a couple of assumptions about this process. So I'm going to list down our assumptions. We can assume the process is isothermal. So the temperature doesn't change. So we can write down, so the output temperature is equal to the input temperature. And what that means is the internal energy of nitrogen gas doesn't change. There's no energy imparted to the nitrogen molecules. All of the work is done towards compressing the gas. And we're going to assume the gas is ideal gas. So work done is simply the area under the curve. And from calculus we know that area under the curve is equal to So from calculus we know the area under the curve is equal to is P TV going from V1 to V2. We also know if we just invert the variables, this is equal to V dP P1 to P2. So I did this variable conversion because I know P1 and P2, and I don't know V1 and V2. So this is just to make the math simpler. So now so P1 in this case is 1 atm, P2 is 10 atm, and then V from ideal gas law, V is equal to nRT over P. That's from ideal gas law. So I can plug that in here. So here we assume the temperature is constant, and therefore this entire numerator is constant. We know that N is the number of moles, which stays the same because R is a universal gas constant, that's a constant, and temperature, as we said, we're assuming isothermal process. So we can take the entire numerator out of the integral. So when we integrate 1 over P, we get ln of P. Let me go ahead and correct that. So we know from calculus this is equal to minus of that. So that's not critical, but just to make sure that our math is rigorous, we'll just put that negative sign in there. And I'll move that negative sign right here. So we know that work done is equal to nRT. So finally, we get our negative of work done is equal to nRT ln 10. So I'm going to go ahead and box that. So I'm going to go ahead and use the next slide to continue working on this problem. So again, our work done, negative work done, is equal to nRT ln 10. So we have to compute each of the three variables. So we know N for nitrogen is equal to 1 kilograms divided by the molecular mass of N2, which is 28 grams per mole. So if you compute those numbers, number of moles of nitrogen turned out to be 35.7 moles. We know R, the universal gas constant, is equal to 8.31 joules. We know the temperature is equal to 20 degrees Celsius plus 273 equals 293 Kelvin. So we plug in all the variables. Negative work is equal to 35.71 moles times 0.31 joules times temperature is 293 Kelvin times ln 10. Plug in all these numbers, we get 228.7 joules. That's equal to, we can approximate that as 200.2 kilojoules. So if we go back to this previous slide, we know we found our input and we already knew our output. So now we can getting closer to our efficiency. So one of the things we have to do is we have to convert everything into the same units. So we have to convert input in joules, which we've already done. So the input is 200.2 kilojoules. Convert everything into joules. So our output, you know already, is 200.2 kilojoules. Our input joule is 250 kilowatt per kilogram. So when we computed our output, that was computed for 1 kilogram of nitrogen when we compute a number of moles, and that was computed for a time period of 1 second. So again, we can do 1 kilogram times 1 second. That will give us 250 kilojoules of energy. So that's our input. So our efficiency is simply output over input is 200.2 over 250. That number simply is 80%. So let's go back and rethink this problem. So when we computed our output, we computed assuming isothermal process in ideal gas. So that's a reversible process where all the energy provided by the compressor is transferred to the gas in terms of compression work, and no energy is wasted in terms of heat. So that's the minimum amount of energy that a system will need. However, we find that the compressor actually needs more than the minimum. The compressor needs 250, whereas the work it does is actually 200. So the difference, we'll compute the difference here. Difference between the input and the output here is approximately 50 kilojoules of energy. And that energy, as you might predict, is wasted as heat. So the nitrogen gas actually might not be 20 degrees Celsius when it comes out. It might be a bit at higher temperature. So that's it from this video.